Hey everyone, thanks for watching. In this video we're going to look at a container that was full of ice and then we put it on a hot plate and decided to melt the ice and bring it to the boiling point. The graph that you're seeing over on the left is synchronized to the video. So when you watch the cursor move across the screen, you're seeing what happened to the beaker in real time. Now we have three kind of strange mysteries here. One is, why does the temperature stay completely flat for the first minute and a half, even though the hot plate is turned on? The second mystery is, why is the temperature going up and down, according to our digital temperature probe, in the next 3 to 4 minutes? And our final mystery is, after it reaches boiling point of about 100 degrees Celsius, why does it stay at 100 degrees Celsius for the whole time? Let's tackle the middle mystery first. As you can see, I piled the ice really high, and as I move slowly across the graph, and the ice is melting and falling into the beaker, it's starting to cool the water down just as it's starting to heat up at the bottom of the beaker. And so it's no wonder that the temperature falls. The ice is from above the temperature probe is falling in and cooling it off. And then once all the ice is nearly melted, the temperature of the water really starts to take off. And it continues all the way to the boiling point. For that, let's switch over to some illustrations. A moment ago, we were looking at this graph of the temperature versus the time. Hey everyone, thanks for watching. In this video, we're going to look at a container that was full of ice. As it started off as a beaker of ice, the temperature was very flat and it didn't increase. And then the temperature became a little bit bumpy. And then at the very top of the graph, the temperature stayed flat again. So we want to talk about why that is. But before we do any of those things, let's talk about what temperature actually is. That's a strange question, right? Like we talk about the weather and talk about what the temperature will be tomorrow, but what is temperature? What are we talking about when we take a thermometer like this and we stick it in a beaker of water? I like to think of temperature as kind of like the radar gun that a police officer would use on the side of a highway. It's actually measuring the speed of the particles. When particles are moving faster, they have a high temperature. When particles are moving slower, they have a lower temperature. But there's trillions upon trillions of particles, even in a small sample of water. So really what we're saying is, we're taking the average speed of the particles that are in contact with the temperature probe or with the thermometer. Now, let's set these aside for a minute and talk about what's happening with our ice as it gains heat. Here I've put together a model, and this model represents how the particles in a solid are arranged into a pattern. Now, this is a stable pattern, and they want to stay this way. But when heat energy is added, it begins to disrupt that pattern. And even though these particles are wiggling in place ever so slightly, they are not really truly moving around. And then once we disrupt that pattern, that structure, that order with the heat energy, then these particles will begin to move around and become the liquid water after all the ice has been melted. And that's the point at which these particles can move further away from each other with all their new heat energy, and their temperature can rise. So until we have released them from this pattern of arranged particles, all the heat energy goes into just releasing them so they can move more freely and become a liquid. Let's talk about what's happening on the other end of the graph. Up here is where the temperature stays constant as well. I've made another drawing here, and this represents the beaker full of water, and these temperatures represent the temperatures of the particles. Remember we were saying before that temperature is just the average speed of the particles. These particles average out to just below 100 degrees, or maybe they average out to exactly 100 degrees. And when we put the temperature probe in the water and we are heating it, we see that the temperature doesn't rise. That's because some of these particles gain enough heat energy that they rise up off the surface and they become water vapor. And what that means is the hottest particles have left, and what stays behind are particles that have the same average temperature. All of these numbers here still average out to just below 100 degrees. So they have the same temperature. We cannot make the temperature go up because none of these particles go above 100. Once they go above 100, they leave the beaker as water vapor. So, in conclusion, adding heat energy increases the temperature because it makes the particles move faster. Knowing the average speed of the particles is what we call temperature.